All right, everybody. This is going to be the conclusion of our discussion for the 22nd of November. I'm going to be talking about transport of substances across the membrane. And then I'm going to talk about sodium potassium ATPase. So to get things moving, though, I don't know why it's doing that. Okay. I want to go ahead and start out by talking about transport of substances across membrane. Now, the first thing that's important to understand is that you can look at the diffusion of a substance or the movement of a substance between two sides of the membrane, either interior to exterior or exterior to the interior, and how it resembles a chemical equilibrium. Now, if we look at A is the substance. It has a starting position or a source, and then it has a destination, the place that it's going to. So we can look at this almost as a chemical reaction. A source goes to a destination. Now, the difference in the concentration of a substance on two sides of a membrane generates a chemical potential difference. So if, for instance, a substance is going from a very high concentration to a low concentration, then that's going to be a favorable movement. So high concentration to low concentration, favorable, as opposed to from a low concentration to a high concentration. So what we can do is we can look at our chemical potential as delta G, I apologize for yawning, is equal to RT times the natural log of the concentration of our substance in our destination versus the concentration and in the source. So the final position or the product over the initial or your reactant. Now, the movement of ions across a membrane also, because key word there is ions, the movement of ions across a membrane also results in a charge difference generating an electrical potential difference. Okay. So we can look at the electrical potential difference as Z sub A times Faraday's constant F times delta psi, which is what's known as the membrane potential. So we can combine those two things to come up with an electrochemical potential. So with this electrochemical potential equation, we're looking at the delta G, or the free energy change, considering both the chemical potential as well as the electrical potential difference. So is this a movement that's favorable from the perspective of, is this favorable from the movement, or from the perspective of, is this going from a low concentration to a high concentration or high concentration to a low concentration? In addition to that, what's the significance of this ion moving from one side of the membrane to the other side of the membrane? We come up with this equation, or this equation, delta G equals RT times the natural log of A, your substance in the destination, divided by A, your substance's concentration in the source, plus Z sub A, which Z sub A is simply the charge on the ion. So if it's a magnesium ion, that's going to be a +2 cation. A sodium ion would be +1. Times Faraday's constant, which has a value of 96.485 kilojoules per volt mole, or 96,485 joules per volt mole, times delta psi, which is the membrane potential, which is measured in volts. Okay. Now, the membrane potential is measured by default as the potential inside the cell, the destination, minus the potential outside of the cell, or the source. So we're comparing the delta psi is the destination is inside and the source is outside. So anytime you look at a delta psi value, that delta psi was calculated based on, or it is based on, an ion moving from the outside in, as opposed to from the inside out. Now, negative number indicates the inside of the cell is more negative than outside of the cell. If an ion moves from the outside to the inside, then the membrane potential is fine. So you do not have to worry about changing the sign of that delta psi. On the contrary, if an ion moves from the inside to the outside, then the sign of the potential must be changed. Okay, so almost always the cytosol is considered to be the inside of the cell, of course, or the inside destination. Of course, this could vary if you're talking about like a mitochondrial protein or a protein that is involved in transport of ions all across any other membrane. Okay. If more than one ion is transported, you need to calculate the free energy change for one ion and multiply for additional ions. So ultimately, this leads to a question like, is it favorable from a charge standpoint to transport chloride ion, Cl minus, into a cell when delta psi is equal to negative 60 millivolts? Okay, so that delta psi, that's a measure of the potential that that specific membrane provides. So you could almost think about that as like a constant of sorts. So negative 60 millivolts. Millivolt would be, let's see, 0.060 volts, because 1000 millivolts is equal to 1 volt. 60 millivolts is 0.06 volts. Now, after that question's been answered, what about the reverse? So we're talking about moving a chloride ion from the exterior to the interior. So if we go back to this, this says, or this slide says, by default, delta psi is measured as the potential inside as your destination minus outside, which is our source. So our source is outside, our destination is inside. If an ion moves from the outside to the inside, then the membrane potential is fine. This specific example is talking about, well, moving an ion from the outside into a cell. The second example, what about transporting it out? Well, then you'd have to take that negative 60 millivolts and actually come up with a positive 60 millivolts. We'll get to that in just a second, but what I want to go through is a way to calculate this. Okay. So, or a way to calculate this sort of problem. Now, what if we're transporting sodium in or out of the cell when delta psi is negative 60 millivolts? We have a cytosolic concentration, which is the interior concentration of 12 millimolar, and we have an exterior or an extracellular concentration that is 145 millimolar. Now, the first question here is, what is the change in free energy associated with transporting sodium into the cell at body temperature of 37 degrees? Now, with all this in mind, I just like to think about this as, where are we going? This is asking us, what is the free energy change, or what is the change in free energy associated with transporting into the cell? Okay, so we're going from the extracellular to the cytosolic space. Now, the extracellular concentration is 145 millimolar. It's a very high concentration compared to the interior concentration, or the cytosolic concentration, which is 12 millimolar. So if we're moving from the outside in, we're going from a space of high concentration to a low concentration. So without doing any sort of calculation, would you expect that to be a favorable move for your sodium ions? Well, if we're going from a high concentration, so an environment where there's excess sodium, to a low concentration, the cytosolic space, well, then I would say that that is a favorable move. From high to low, that's a favorable movement. Okay, so now we can calculate this chemical potential. This is calculating our chemical potential. We'll then use that to calculate our electrical potential and combine them to calculate our electrochemical potential. Our chemical potential is 0.008315 kilojoules per mole. So that's your R value. Our temperature Well, it's 37 degrees, so 310 Kelvin. Natural log of our destination over our source. So the destination, which is the cytosolic space because we're going from the outside in, 12 divided by 145 is equal to negative 6.42 kilojoules per mole. This is a kind of, if you round these numbers, it might be a little bit easier to play along if you feel comfortable with these log calculations. Now, with that in mind, what's the electrical potential? The electrical potential. So this right here is this right here, the first part of our equation. The second part of our equation is Z sub A times Faraday's constant times delta psi. So Z sub A is the charge of our ion, which this is a sodium ion, so it's +1. 96.485 kilojoules per mole volt. Well, then we've converted, let's see, we've converted, okay, so kilojoules per volt mole, okay, so 96.485, that's Faraday's constant. Then our membrane potential is negative 0.06. Well, the membrane potential needs to be changed from millivolts, which it was, into volts. So negative 60 is equal to negative 0.06 volts. One, our charge of our sodium ion times 96.485 times negative 0.06 give us a SA value of negative 5.79. So essentially, you can look at this as, well, it's favorable to move the sodium ions from the outside in from a chemical perspective because of our difference in concentrations. It's also favorable from an electrical standpoint because we're moving that one ion and we have a membrane potential that is negative 0.06. So all told, we end up with a delta G value that is negative 6.42 plus negative 5.79 or 12.21. I apologize. So negative 12, this is a favorable movement. So these sodium ions going from a high concentration to a low concentration, favorable. Now, as just a little bit of an exercise, if we switch the ion from a chloride ion or from a sodium ion to a chloride ion, would it be favorable? If nothing else changed, well, that's kind of tough. If nothing else changed, it would still be favorable from a chemical perspective. But from an electrical perspective, then that would end up being plus 5.79. So negative 6.42 plus negative, or plus 6.79, you end up with something that's still slightly negative, but a little bit less. Okay, so now if we did the opposite, if we were moving these sodium ions from the outside or from the inside out, what's going to change? Well, our source and our destination and our chemical potential calculation are going to be different from one another. It's going to end up with 6.42 kilojoules per mole. Our electrical potential difference, 1 times 96.485 times 0.06. Well, again, the thing that we need to consider is we did change our delta psi, but we need to go ahead and change it to a positive value because now we're talking about moving from the inside of the cell to out. So we're expelling that sodium. So this ends up with, whenever we talk about moving sodium from the inside out, it becomes much more favorable overall and ends up with a very positive value. Or sorry, much less favorable than it's a positive value. Okay, so now what's the change in free energy about transporting 2 sodium ions out of the cell? Well, it would be that delta G is 12.61 kilojoules per mole. Multiplying up by 2, you get 24.42. Okay. Now, sodium potassium ATPase. So anytime you look at a pathway like this, the most important thing is to be able to visualize what it is that you're talking about. And in order to visualize it, I think that the best thing for you to do is to find a starting place. Now, a couple of things that you need to know. The key to the sodium potassium ATPase is the phosphorylation of one specific amino acid. Now, what's a little bit odd about this is when we talk about phosphorylation, we talk about histidines, serines, threonines, and tyrosines. Those four players are the ones that we most commonly see get phosphorylated. In this case, we have an ASP or an aspartic acid that's actually getting phosphorylated. And it's getting phosphorylated very early on in the process. Now, ATP phosphorylates the transporter only in the presence of sodium. The aspartyl phosphate residue is subject to hydrolysis only in the presence of potassium ions. Okay, so this is a very, heck, those two lines basically sum up the entire pathway or the entire model. So what this first item is ATP phosphorylates only in the presence of sodium. So we have E1, which is our transporter protein. That E1 is going to bind ATP, and you know what it's going to do? It's going to phosphorylate itself, and that ATP is going to be released as adenosine diphosphate, or ADP. That phosphorylated E1, indicated right here, was only generated because of the presence of these sodium ions. So this is the insides, or the inside of the cell. We have on E1 a phosphorylated aspartic acid. Now that E1 is going to be able to undergo some transport or some conformational changes. And whenever it undergoes that conformational change, these sodium ions, well, they will end up on the other side of the lipid bilayer. What that leaves behind is we have kind of a new form of our enzyme. Rather than E1, it's referred to as E2. It's phosphorylated still at that aspartic acid, but it's no longer binding sodium ions. Instead, what can happen now is our potassium ions can find the binding spot on E2, the phosphorylated form of this protein. So on the outside of the cell, we have E2, which is phosphorylated, which also has two potassium ions. Once that is more or less stabilized, there's going to be the hydrolysis of one or that phosphate group off of the aspartic acid. So that aspartyl phosphate residue, which is illustrated in the upper left-hand corner, is going to be no more as of this point. So yoink, despite all the great work that was done in order to discover this, there we go. Now, the result is we have a E2 form of our enzyme, which is bound to two potassium ions. Those two potassium ions are ready to go and be released on the interior side of the lipid bilayer, or on the interior side of the cell. So the sorts of questions I like to ask about this are, one, which amino acid? Why is that kind of interesting? Well, it's because none of the other amino acids that we talked about that get phosphorylated by aspartic acid. Two, I think that it's very cool that these three sodium ions are basically traded off for potassium ions, and it's because of this phosphorylation. So those are some of the cool things about this. Those potassium ions, when they're deposited inside the cell, well, then there they are. That is going to release E2, and now we have E1, which is going to be able to have the sodium ions in that solution and bind up and associate with that E1 protein. All right, everybody. Well, I hope this was helpful, and I hope you have a good day. And I'll just make sure, yeah. This last item here is just illustrating the affinities that each of our proteins have. When sodium ions are present, now all of a sudden E1 wants to find ATP. E2 has a low affinity for sodium, but a very high affinity for potassium. So it's going to be able to select the potassium ions in the absence of the sodium ions. All right, everybody. Have a good one.